great time for us to learn about propellers and governors, is it not? It is, right. Okay, so real quick, we'll talk about prop and governor theory before like a little bit of design and operation. So propellers, pretty obvious, right? We all know what the propeller is on the aircraft. And then the governor is basically an engine accessory that was invented to regulate the pitch angle of your propeller blades. And what it does is if you regulate the pitch angle, what you can do is change the load that you put on the engine, which regulates engine speed or RPM. Yeah.
Are governors only used for constant speed?
The governor technically makes it a constant speed because you can tell the engine what RPM you want, and then the governor changes the blades back and forth to get that engine speed. So yeah, it regulates speed. Like governors, most oftentimes you'll find them on like smaller engines regulating RPM, like lawnmowers, golf carts always have governors on them. But yeah, it's known as, that would be a constant speed or a variable pitch, because you can change the pitch of the prop. Constant speed, variable pitch, same thing. So then as I move, it should move with you guys too on your screens. Here we go. Props. Okay, so what is the role of the propeller in relation to the engine? Well, we're turning brake horsepower into thrust horsepower, which brake horsepower, if you didn't know, is a way that we can measure the power created at the engine, right? And then we lose some of that power as it goes places. Like we lose some of it as it goes into the prop. In a car, you lose a lot of it through like the transmission gearing, the axles, traction with the ground. You don't get all of your horsepower right to where you want it. I think it was something, it was like 40 to 60% of the brake horsepower makes it into thrust horsepower, just in terms of like efficiency. But yeah, pretty simple. Okay, so our propeller is an airfoil, and it basically works the exact same way that a wing works, right? Wings, imagine these are my wings, right? It's the exact same shape, but instead of flying this way through the air, we're just rotating it around. What else do we do that looks like this that's really similar in terms of like rotating an airfoil? Anybody know? That was a poorly worded way to ask it, but. Yeah, which are called what? In terms of like the class? Rotorcraft. Yeah, because you're just spinning your foil rather than mounting it and going forward with it. So here you can see, I'll refresh your memory from intro to aviation and ground school and all that jazz. As air flows around our airfoil, it splits, right? What's important to remember is, say we had two molecules, they split around this airfoil. The one on the top is going to increase speed, which decreases pressure, right? And then the one on bottom is going to decrease in speed and increase in pressure, but they make it to the back of the wing at the same time. And so on top, we have basically a ton of suction. We have a large vacuum that is maintained on top of our wing, and then on the bottom we have high pressure. So your wings are not only getting pushed up, but they're getting sucked up, right? And your prop does the same thing. As it's ripping around in front of you, it is creating a vacuum right in front of itself, and it is sucking the plane forward into that vacuum. And then on the flip side, you're creating high pressure on the back, right? Which is pushing you forward. So, quick review on the airfoil. I think this is the gift. Yeah, this was sweet. I saw this. It's I don't know. They somehow like using the imagery for pressure underwater at a boat propeller, and you can see like here. I mean, that's like the angle's kind of funky. But you can see on the leading edge the vacuum like working its way all the way down the edge of the prop, and then on the backside, as the tips of the blades come around, you can see the high pressure forming behind it. Right? You have vacuum on the front, pressure on the back. See this blue cone coming out? Do you know what that is? You know?
Is that a vortex? Like the center of a vortex being formed by the prop?
Yes.
Like cavitation?
Yeah. That's what we want. Cavitation. Cavitation happens underwater really easily. What do we call? Man, that's not right.
Turbulence almost.
Yeah, it's like
You can
turbulence.
see the rings on the bottom there at the top.
So cavitation happens in liquid especially. It's when you have rapid separation. You create a vacuum underwater. You create a bubble actually out of nothing just by separating the fluid molecules. And then when they come back together, it smacks and claps like real bad, and it's actually super dangerous. Like cavitation in like a fuel pump or like a water pump or anything like that, when those air bubbles collapse, they can break metal. Can get pretty gnarly. Okay, moving on. Alright, propeller parts. We're going to talk about the descriptors of the propeller. Propellers are made of multiple blades, right? But your blades can also be, you have your blades and then the hub in the middle. That can all be one solid piece, or it can be modular. We have blades that are like mounted and bolting into the hubs. Your blades are almost always going to be identical. Well, they will always be identical. Why?
Because they're different routes symmetrically. I mean, each of your playing parts.
Balance, super important. And if you don't have it, especially at the prop, like this is a huge piece of metal. We are spinning unreasonably fast, right? Like nothing else is, no other vehicle is throwing this much weight around as much as planes and helicopters. And so yeah, it has to be really well balanced, right? Then they're almost always, they have to be light and strong. So we never make them out of steel. Once you get up to like the turbofan propeller blades, those are all, I believe, made of like titanium. But for our aircraft, wood, aluminum, and composite. And then the hub, just super important that that thing has good structural integrity, and it's a massive. I wish you had a hub here, but I got a picture of one for you, where you can just see the two pieces. Here you can see the different cutouts and the curvature of the airfoil and the thicknesses at each one, at each station. So your blade, you have your tip, the shank, and then the hub that it goes into. So you can see that like the amount of engineering that goes into these propeller blades is amazing. Like determining how long they want the blade to be, because as you come farther away from our crankshaft, the farther away we are, the faster the blade is spinning, right? So you're covering more ground, so you have more centrifugal force. And at what point is the airfoil going to start stalling? Because it always stalls, I think it stalls outboard first? How does a wing stall?
Inward to outward.
But I'll kind of pass this around, let you guys throw it around. This is incredibly thin. Like it would not be hard if you sharpen this. It would be quite a blade. And when your propeller, this isn't cast. I'm not sure. I can't remember how it is. I think it's all like milled out of one piece. And it's really strong. These they'll bend, but they'll also rip. Like, say I have this piece of paper, right? I can pull tension on this piece of paper and it'll take quite a bit. But as soon as I put a little tear in it, in the edge, and then I start pulling tension, what's gonna happen? It's gonna wanna split in half and fail at our weak link, right? The equivalent to that in aviation is like a nick, or you hit a rock or a stick when you're taking off on the grass. Or, like that's why pilots, a big part of your pre-flight is you walk around and you check the prop. And I always take my fingernail and you run your fingernail. If it catches on anything, or like when we're doing maintenance, if it catches on it, then you know right there's one. That's got to be filed and sanded off of the blade because it's too much of a imperfection. And that's just because the blades get so paper thin, and then they're spinning so fast, you have a lot of centrifugal force. But this one had a boot on it too. You can see the glue right here. So this was an electrical heating component. No cycle on and off. It prevents ice building up at the shank of your blade. Because at the tip it's moving so fast, it's not going to build ice. But down here it will. And then when that ice builds up, then you have extra weight and then it's not balanced properly. You ever like drifted into a snowbank in your car? And then you start driving down the road and your back tire's going and you're like, oh, I hope I didn't break anything. And then like 30 seconds later it's fine. That's because you drifted into a snowbank and your whole wheel just got packed full of snow. And then you start driving and then you have like, you know, even if it's only like 4 or 5 pounds of snow in there, it's getting thrown around, it's not balanced. And like even ice, like when I lived out west, in the winter you get like, your wheels would freeze to the ground. And you get like ice chunks in your tires that would shake till they'd fly off on the highway. So, yeah, balance is pretty important. Let's go to this slide. This says challenge draw. Let's skip this one. But this was like an interactive thing, I think. Is it working for you guys?
Time
It
for
says
us to
we're
draw
waiting.
it.
It says we're waiting for you to send it.
What do we have to draw?
Just wait for your teacher.
Wait.
I need to get it started somewhere. Where do I need to start? Instructions.
Yeah, instructions maybe. Open whiteboard. Hey.
Now we're seeing what you're doing.
Yeah, this is no good. Close whiteboard. Alright, we're moving on. Okay, this is a typical hub. Right where you just have just massive cast aluminum and steel pieces that hook the blades. And then they usually have oil pressure contained in them, and a big old piston moves forward. So like your governor would be like somewhere around here, and then you'll have a piston that your governor pushes, oil pressure cycles it forward and back, and as it does that, all the blades. Yeah.
Why is there something masculine tape for the aircraft?
That looks like an engine block heater. Well, more specifically, an extension cord that the engine block heater is plugged into.
Gotcha. So it's like a full thing that kind of went out the engine hub.
Right, it's like electric heating
Yeah.
that's glued to your oil pan, and then they have ones that you can clamp around your cylinders. So you can go plug, say like you want to go fly this cold out, you can go plug your engine in, and then do 20 minutes of like pre-flight, flight planning, go to the bathroom one last time. Then you go out to your plane, you unplug it, and the whole engine block is going to be like 150 degrees, and the oil's going to be nice and hot. Start it up, no problem. It's more of that, because cold starting these engines are so big, like the pistons,
Yeah.
and cold starting these little things can be really tricky. So you can just heat them up.
Yeah, so
Okay, this I believe. Oh wait, yeah, no, this is a typical hub. Just quick picture here where you can see all the pieces that will lay into it, and then they still have their ability to move. All right, this I think you guys have access to move through these photos. Here's like very typical one-piece propeller. So the blades and the hub are all one solid piece of aluminum. All the propeller bolt holes are milled in. Let's see, wooden propellers, you'll have like big metal washers as like a faceplate for bolts. But wood props actually will swell just like any wooden structure or wooden home with temperature and humidity. So in the wintertime, you have to retorque these bolts because the wood shrinks in the winter. And so then in the summertime, you gotta loosen them up and torque them down to a less torque value. Yeah, triples. Yeah, once you get into like big turboprops, I'll talk about those in a second actually, but this would be typical on a big turboprop engine, like that on the Pilatus or like a PT6. These blades, so they'll feather. What that means is like normally, say I'm flying this way, right? Normally my blade is gonna be at a pitch angle somewhere around that. Okay, but if my engine dies, this is gonna cause a lot of drag. Here, let me put it up this way. This causes a ton of drag if my engine quits. It's the equivalent of me sticking my hand out on the highway, going like that, right? It's much more smooth if you go like this. If you go like that, it stretches out your shoulder or whatever. So they're called feathering. So usually, we're cutting through the air at a nice pitch angle like that. We have an engine failure. Oh crap, we need to glide really far. Let's feather our prop. So boom, now we're gonna put our prop like this, and it's much more streamlined, right? So we're creating way less drag, trying to get to our safe zone. These big engines, you can then go past feather into what's called beta. So this is forward, feather, and then they'll just go beta, and they'll just go straight backwards. Basically what happens, like when this goes into feather, it's just a huge wheel of canoe paddles, right? They don't do anything, they're like sitting there, flapping around. When you go into beta, now all of a sudden our engine is spinning, but instead of sucking air from the front to the back, we're doing the opposite, because we just twisted the blades all the way around. So they basically just go in reverse, and you start pushing air forwards, and it just creates a ton of turbulence, and the aircraft slows down. And these big turboprops, you see them coming to land. Like this guy that used to work right next to us, he was a crop duster, and he would always land like, and then get off by the first taxiway, so he would land in like 1,000 feet. They're coming in on final, he's real quiet, right, because he doesn't have much power in. And then as soon as he touches down, you can hear him go into beta, so then the props feather, because they're still spinning, you can hear him get turbulent, and then once it's in beta, he goes full throttle, and so it comes into land. You can hear this on like bigger planes too, but they don't have props, they have vanes that open up into reverse. But the plane comes into land, and then as soon as it touches down, it's like, and it gets like really loud, and you just hear all this like fake thrust going nowhere, and then it quiets down again as it like rolls off. And that's them, they have to throttle up in reverse. And most every time reverse is just coming from either a prop or like on the two posters hanging on the walls up here, those are most likely clamshell reverse, where just like
two big things come out and redirect it. Back to a jet ski or something. Okay, what else we got? This is like a little carbon fiber composite prop that's being made. Maybe I'll show you guys afterwards, but yeah, these are pusher props. You guys have seen Cliff Main's lake amphib that's out here, and his has a pusher prop on, you know, the end, the engine on top. Yeah, so same engine function and operation, just the propellers are backwards.
So, on the, like, on your pusher prop picture you had there, it's got the canards on the front. Does that help more with the pusher as opposed to a polar style aircraft?
I don't know. I'm not a aerospace engineer. That's totally like a balance and a control and a, like the designing,
Yeah.
having your like thrust, I don't know, coming from like where's your center of gravity, your center of balance, or yeah, I don't know. And then on the ground, like how tail heavy is it on the ground? Because this guy's not doing he's not doing his job unless he's trying to push. Yeah, see, I don't know. I'd have to
Push into the center of pressure.
Is this thing creating lift,
I'm an aerospace engineer, what do they say?
or is it going down? Wings are pushing up, tail's pushing down. Is this pushing up or down?
I'll keep the nose levels or down.
Both. Is it just an elevator? might just be an elevator.
I think that's like flying in a patch. It's just acting as like a second airfoil.
Yeah. Like these guys?
Yeah.
Yeah. Yeah, I don't know. We have to do some homework. We'll try to build one. Another thing I wanted to mention is the markings on the prop. You'll notice that they almost always have white or yellow on the tips of the blades. That's a visibility thing, so when the prop's spinning, you see big old circles so you don't have to walk into it. Because when it's spinning, it's like invisible. And then on the flip side, the back is always matte black. Because if you do have a big old prop spinning in front of you and you're at 10,000 feet and you're trying to look around, if this is like a nice polished shiny aluminum and the sun is behind you, you're gonna be blind like the entire time you're flying. So props on the back especially will need repainting. You can feel all these chips and scratches. Yeah, and so as mechanics, it's our job to dress them, which means you dress it with like a file and some sandpaper, make sure it's all smooth, continue to paint it nicely, and inspect the cracks. Alright, we were talking about governors. This is a great image to show you what the governor does. And that is pretty much the extent of the movement on our small engines. Like this will be our spinner, the nose cone, right? So we're flying this way, and the governor lets our prop go from this to that. Pretty sweet, right? Okay, so the pitch of our prop is, imagine, the reason we call it pitch is like, you know, when you're flying, you're pitching up and down, right? It's the same thing. We're worried about our angle of attack, our relative wind. Okay, an airfoil, the greatest threat to our airfoil is a stall. Whether it's a helicopter rotor, an aircraft wing, or a propeller. Your airfoil can do a lot of good work for you, only if you have the right angle of attack. Because if you stall it, you know, we're gonna fall. So, what we want to do is be able to adjust our propeller pitch, and that can let us operate efficiently at different air speeds. Imagine this governor basically as the transmission in your car, right? In your car, when you hit the gas, when you're at a red light and you hit the gas, your engine goes from 0 to like 2,000 RPM, okay, and then it shifts and it goes back down to 500 or 1,000. And then it takes you through that same range of motion every time it shifts. The propeller, imagine the governor gives you like 2 gears. Say you have a fixed pitch propeller, which would be one of these. This is fixed pitch. You cannot change it ever. You buy it, it'll get the job done. Also, props are like non-transferable. You can't just like, oh, this is a nice prop. I think I'll try it out and put it on your plane. It's like they're all measured and classified for specific aircraft. So basically, at different air speeds, we want to have set RPMs because the pilot has to be able to control RPM to be able to control fuel burn and know that they can make it to where they're trying to go. So we're trying to control the engine speed, not which relates to our prop speed. Basically, by changing the bite of the prop, which changes the load that we put the engine under. This image here is really helpful to understand. The finer corkscrew is when we're at lower air speeds, which would be that most of this is like we're considering that in these that we want, like the flight characteristic that we want is always going to be at like full power or cruise power. So takeoff is almost always full power, and cruise is just less than full power, to be honest. And so when we're on takeoff, we want to still use up 3,000 RPM because that gives us the most amount of power. But we do it by taking lots of little bites out of the air because we're not moving very fast. So we want to be spinning really fast, and so we take tiny bites, lots of tiny bites. That's how we take off. And then we get up to altitude and we want to go fast. What we do is we just open up our jaw a little bit more. So we're taking bigger bites now, but our engine is still spinning at 3,000 RPM that we wanted. And this is how the governor works. This is what it looks like. It's basically flyweights, which are, imagine it like, flyweights are like a gyro, right? You get weights spinning around, and as they react to relative motion, it gives us like a reading or an input or something. So basically, as your prop is spinning here, attached to the crankshaft, via this little spline, this would be, here's our crankshaft going forward, here's our 2 props. A governor, sometimes it is its own little oil pump, sometimes it just uses oil pressure from your oil pump. But as those flyweights spin around, which are like directly connected to the crankshaft, so they're working at the same speed, as those flyweights spin around, they will lean outwards and inwards based on how fast they're spinning. And when they do that, the thumbs push up and they adjust the valve, which lets oil flow up into the hub of the prop and move the piston. All the blades will twist. So instead of me continuing to yap, I'm going to show you this awesome quick video where this lady explains to us why somebody is a billionaire because of the invention of the governor. Not really, but it is a really, really
Planes have a fixed pitch propeller that is designed to operate most efficiently only at one particular airspeed and engine RPM combination. The propeller blade has the optimum angle of attack at this airspeed. However, as the airspeed increases, the angle of attack becomes smaller than optimum, and as the airspeed decreases, the angle of attack becomes greater than optimum. The variable pitch propeller was developed to address this problem. Its blade angle can be changed from fine to coarse or any position in between. On modern airplanes, this is known as a constant speed propeller. It allows the propeller blade to maintain the optimum angle of attack as the airspeed increases and decreases. The blade angle changing mechanism is operated hydraulically with help from a device called the governor. The governor is driven by the engine crankshaft and consists of rotating flyweights. The governor forms part of what's called the constant speed unit. The governor flyweights are engine RPM sensitive. So as the engine RPM increases, the centrifugal force moves the flyweights outwards, and as the engine RPM decreases, the flyweights move inwards. The pilot can control how much the flyweights move through a blue lever called the propeller pitch control. This lever sets tension in a spring attached to the flyweights. It allows the pilot to reach a target RPM, which the constant speed unit will automatically try to keep constant in flight. The governor flyweights are connected to the pilot valve. This valve acts like a gate that directs fuel to or from the propeller hub, which in turn sets the required propeller blade angle, which in turn sets.
Okay, so pilots have 3 controls. This would be considered a high performance aircraft, which is anything that is over 200 horsepower, has retractable landing gear, or has a constant speed prop, which means that you have a prop pitch lever. So the pilot has a throttle, a mixture, and a prop lever. And you can set, like she's about to explain, a certain RPM. And then what you're doing is setting a preload tension on this spring, and then the flyweights control, which is really funny, she's Australian, she says, flyweights. And then the flyweights will control this pilot valve and either let pressure in or let pressure out, and it naturally adjusts. And then as this changes, the RPMs change, which changes your preload, and the 3 are constantly pushing on each other and making sure that everyone's happy.
The required propeller blade angle. Let's have a look at a couple of examples of how the constant speed unit works. This is a step-by-step breakdown of a process that happens quickly, continuously, and automatically. The propeller pitch control set back, the pilot requests a lower target RPM. But if the aeroplane pitches down, for example, the propeller wants to speed up, thus the RPM wants to increase.
Okay, wait, why? Why is it that when we pitch down, well, when the pilot pitches down, why does our engine RPM increase?
Well, the second one I think is, as I'm going down, there's more air pushing on the prop, which causes it to spin faster.
Yeah,
It's like blowing on a fan.
yeah, exactly. And we can easily overspeed the prop, actually. You can overspin your engine doing that. And it's also, another reason is because now we're doing less work because we're rolling downhill essentially. And so our engine was set, we had a certain amount of gas and air that we were giving it, and it was working, and now all of a sudden we take its work away and it's, it just starts running fast.
The flyweights move outwards, open up the pilot valve, and allow oil to flow into the propeller hub.
So our
The
engine
blade
is
angle
speeding up.
increases so the propeller takes a bigger bite of air. This requires more engine torque, so the RPM slows down and the flyweights move to their equilibrium position.
And our pilot valve closed.
The pilot valve closes and the blade angle and engine RPM is maintained. With the propeller pitch control forward, the pilot requests a higher target RPM. But if the aeroplane pitched up, for example, the propeller wants to slow down, thus the RPM wants to decrease. The flyweights move inwards, open up pilot valve, and allow oil to flow out of the propeller hub. The blade angle decreases so that the propeller takes a smaller bite of the air. This requires less engine torque, so the RPM speeds up and the flyweights move back to their equilibrium position. The pilot valve closes and the blade angle and engine RPM is maintained. The main benefit of the variable pitch propeller is that it provides peak performance at every phase of flight, from takeoff to landing. The pilot can select the RPM that provides the most suitable power for any situation. This improves fuel efficiency and reduced strain on the engine.
Okay, then I think you guys have a question. A fixed pitch propeller, like a big one piece, those are set to do one thing or the other and not really both well. Like the two jobs, one is cruise and one is climb. The Carbon Cub, what kind of a prop do you think the Carbon Cub has? Cruise or climb?
No, climb actually, because it's a smaller air push aircraft.
It's got a climb prop because of that. That's the kind of what they want.
Yeah.
Is to be able to take off out of your front yard and fly to your buddy's house and land in his front yard. Right? So it's like, yeah, we want to be able to just pop right off the ground. But then, like, if you ever see the Carbon Cub fly, it looks like he's just putzing around. It's like, well, that's really only as fast as he can go. But then if you look at this Mooney out here, this white one tucked in the corner, that is a very, very fast aircraft. Those Moonies, they don't have climb props, they have cruise props. So it takes him a while to get off the ground and gain altitude. But then once he's at altitude, he's cooking. Yeah, he's doing good. Yeah.
Random question.
Yeah.
Two of them actually. Number one, when it was on the video, it was showing that pilot valve. The pump that's the oil pump, right? What is that doing when the pilot valve is closed? Because that'd just be sucking on itself, which
Yeah.
sounds weird. And B,
So you have a bypass spring. So as soon as you have enough oil pressure in front of it, that spring depresses and just lets all the oil circulate.
Gotcha.
So same thing. Yeah, it's just a bypass valve to prevent overpressurization.
Right. And then second question was, Mr. Forney up at the main campus wanted me to grab something real quick.
Okay.
You want me? That's fine.
Yeah, go ahead. You come back.
Yeah.
Sure.
Thanks. Sorry about that.
Alright, yeah, you guys got it. Little bite. Yeah, a little smaller bite when we're doing takeoff performance. Okay, you want to hear my analogy that I came up with the sophomores? This is the last thing I'm going to say, and then we'll be done with this. But my analogy for when I was doing it with the sophomores, imagine like, here's our aircraft, and we're flying this way, and our propeller is a knife, and every time we come around, we're chopping a vegetable, right? And imagine you're chopping carrots. Okay, your knife is going straight up and down, right? And you're pushing down, cutting through that carrot. You're not chopping it like that. But imagine that our carrot is like 1,000 feet long, okay? And it's we're feeding it really fast across our cutting board. Like this carrot's moving. You would not be able to go straight up and down, right? Because of the speed of the carrot, what you would have to do is like put a little preload angle on your blade, so that every time your blade comes around, cuts through the carrot that's moving, right? And the only thing that we changed was the speed of our carrot. If the carrot's going slow, we can get it nice, like this, every time. We'll make clean cuts. But if it's going really, really fast, and we try to go straight down, it's gonna push our knife over, it's gonna, little bits of carrot are gonna fly around. We call that turbulence. So what you do is you just adjust the blade of the knife. Boom! Now we can get clean cuts at really fast carrot feed speeds. So that's basically how and why we have crop governors to just pitch, is because you want performance at different air speeds. And you pretty much got two air speeds, takeoff and cruise.